was actual example. Here's a constant force field downward, negative k. Hope you remember that part, negative k downward. And sigma t turns out to be this helix. I don't know if you remember about this helix thing, is that if you compute the speed of a helix, turns out it's a constant speed. If you calculate sigma t, you have calculated sigma t, sigma prime of t, to compute that work integral, right? And it turns out the length of this one is actually constant. It doesn't change, right? So that means the force exerted from that one along the direction of this one, if it is moving like that, let me copy that picture. This is a picture of that helix. For example, if you're in this situation right here, there's a downward force, right? That's F. That causes a certain amount of component orthogonal projection toward to that. So at that moment, this is pushing toward to that direction. So you always feel a little bit of, components coming from the downward force. So you're supposed to get faster and faster. So if I write down sigma t like that, it is not really just going through without friction. If it is like that and the speed is always constant, going toward to that, that means there is a high friction in there. So it's canceling this component out perfectly. All right? So, but it's easy to write this one down. I don't have to put into an increasing speed in there. The formula will be really messy. So I took this one and I just put some, physical explanation to make sense out of it. It actually moves like this with a constant speed because of the friction. And at the end, what I want you to calculate is the total work done by only the gravity force. And there's a friction force is applied in there too. So, set aside that one. Just think about how much work is done by the downward force. For example, if I have something is on the floor, and if I begin to push this one, I apply the certain amount of force, but because of the friction, I wasn't able to make this one excel. I pushed it with a constant amount of force, but it turns out it's moving in a constant speed. That's how you usually, suppose there's a huge box with stuff in it. You pushed it, and you don't really push in faster and faster. You just deal with the right amount such that your thing is moving on the floor in a constant speed, right? So that means the total amount of force exerted onto this object is what? Total force. It's a zero. If it is moving in a constant speed, that means total forces exerted on that one is zero, right? It's because you're putting always some sort of constant speed, but friction is always canceling out just perfectly, and your arm and muscles just feeling that friction perfectly, just dealing with the right amount, make this one move in a constant speed. However, we did some work, right? Using this force to moving this to there. And we have to set aside that the force that's exerted by my arms and with the pushes, how much work is done by me. And there's a friction canceling out, right? So when we're saying how much is work done by the downward gravity force, we set aside friction, get rid of it, just calculate this one. The magic is that you don't have to deal with the actual downward speedy, increasing speedy movement. You can still deal with the sigma prime, right? Which is dealing with the friction. This embeds the friction effect in there, right? But early explanation that it doesn't matter how you pass through, this work calculation, if you calculate it like this, is going to pick up exactly how much work is done by that force, one source of a force. The second source of a force I'm explaining here is the friction. So you completely isolate this one. Here's one source of the force, how much is work done by that? Then you just simply do that integral, and difficult part is that then do we have to deal with the right sigma t, not this one with all the friction embedded in there? No, you don't have to do that. You can still deal with any parameterization because of our geometric analysis done here. Doesn't matter what parameterization you pass through, you use it, this calculation will be the same. All right? That's one explanation and why this sigma prime t is okay to put it in there. And you'll see another explanation later. Okay? So that's the physics side, and lots of things to think about. But mathematical definition of line integral of the so-called vector field is simply just given by this one, and it doesn't matter which parameterization you choose. So actual thing that you have to calculate is easy. Just understand this legitimacy of this definition takes a little bit of a while. All right. So what do you think this total amount of work done by the friction? If they perfectly cancel out and move in a constant speed, it must be the same amount. It's in a kind of opposite sign, right? Yeah. But friction depends on speed. If you move fast, the friction is higher. It is not just position dependent. So I'm not sure how the physicists define the work of a force that is time, depending on your speed. That's slightly different. All right. So I emphasize it here. This part of a calculation. From there, we can understand that for certain segment of a PT, however you parameterize it, this amount will be approximately the same. All right. So that's one explanation. Let me just copy that there. So I think I've explained it sufficient. So I'll move on. All right. This is from the book, and it explains this what we just did. Also, but let me first explain this notation in here. The integral, the force vector dot product of, they didn't use sigma prime t, but they used dr dt, right? So that's a subtlety in there, then I'd like to explain that. Because of that earlier explanation, it doesn't matter how you pass through this one. The work done along that path is always the same, right? By the force. Force is not depending on how fast you're going through. Force, the drag force from the air, that highly depends on how fast you're going through, right? But gravity doesn't care how fast you're going through. Is there always a constant in the position? So that's why this one is independent. And then they're using this r. R is just a position, right? Sigma t is, your position with respect to time. So for that, they use a sigma t. And r is just a simple position, independent of time. But they realize that it is more dependent of your position than how fast you're going through. So they wanted to emphasize that instead of putting the sigma prime t, causing you're thinking that it might depend on your choice of parameterization of the same path. But they put the dr dt in there. It doesn't matter. As long as you have a location in there, however you parameterize it with the t, it'll be the same. So they indicate that with this dr notation, it is a position-dependent quantity, not parameterization-dependent quantity. So there's a little subtlety in there. Switch from sigma prime t to dr dt. dr is parameterized and put dt in there. All right? So this is going to be important. You understand the difference of subtlety with the sigma prime t in there, and to understand later notation, something called, very fancy notion, something called differential forms, right? And this is something I already explained, friction versus gravity. You separate it and understand work done by the separate source of the forces. That's how what this really means. Okay? This two paragraph makes sense? Now this one changes notation once again. So what has changed? They kept the sigma prime t there, right? But F is replaced by capital Phi. That's Greek letter. This is the spherical coordinate little phi, right? And that's a capital Phi. That's a capital letter of that one, a Greek letter. So what is the name of this capital Phi? Vector field. Vector field. And what is the input of this vector field in there? Position, not time dependent. If you have one position in there, whatever the force field that creates the force for that object may be potentially located at that some future. It's going to create this force. If that same object occupies this position, this amount of force will be applied in there. So position, there's a force vector field in there. We have sketched it before. You're putting arrows in each position and things like that. We have done that one. So, not constant vector field. The exercise you did in class for homework was constant vector. I used F, and this one is indicating that every position, different force vector is applied. So, vector field. All right. What's a good example of a vector field? We have looked at this example of vector field and play with it a lot. Whole section was dedicated to this vector field. Anybody remember that vector field? If you have F, it's a scalar function with x, y, z in it. Then we created this vector field. What was that? Gradient vector field. That's right. Gradient vector field creates this, fx, fy, fz direction at each point. This is an important example of this vector field in there. All right? So that means if you have a function, you have level curves, right? The gradient vector field at this point is indicate that going toward to the higher level. That's the meaning of the gradient vector field. The fastest way to get to the higher level. This is f equals 1, f equals 2 in the surface, right? That's the meaning of the gradient vector field, right? So, like the gravity is the potential energy is assigned. The gravity is actually forces going toward to the different levels of the potential energy. Just like a heat flow and things like that. So instead of F, the position it occupies along the motion is absolutely sigma t, right? Here is a sigma t. After t, the position vector from relative to 0, 0, 0, that's sigma t, right? At time t. So that replaced its position as it's parameterized along the curve. Okay? So same thing if the, just the force is varying. And it's emphasizing is a position dependent force. An example of position dependent, this is supposed to be position dependent and velocity independent, but velocity dependent forces are friction is a typical example. All right, so we have that. An official name for this one now is line integral of what? Don't just remember, oh, that's a line integral, but what is more important here is line integral of what kind? Line integral of what? What is it? Vector field. And what was the other kind we'll never study in this course? Line integral of scalar function. We don't consider here, but there is that out there, right? But this is line integral of a vector field. Then what do we do vector field? Dotted with the velocity vector of your path motion. And that's called line integral. Yes?
Is the velocity not going to depend on the vector field? Is the vector field changing the velocity?
No, vector field is position. If here's a position, there is a vector field in there. And the vector field itself is not dependent. However, your motion, this is called free fall in physics. Free fall. There's a vector field. You throw at that position with a ball with a certain velocity to that position. And then nothing else is touching. There's no friction, nothing else, only the vector field. Then if that, after a short period of time, different vectors acting on that, right? Different force. And then it's going to change its direction to something, right? So all the thing is altered by the force field. But the force field itself has nothing to do how fast this thing is moving. This thing is affected by the force field, but force field is not affected by how fast this thing is moving. Affected what? Affected force field. Yeah, but force field is not affected, right? Yeah. But the motion is affected, yes. Yeah. Yes, it's a very difficult actually differential equation. If the differential equation involves a position because it's dependent on the position, and the differential equation involves these two things, right? and all these three things are mingled together, how they depend each other, that's the differential equation. Yes. Spring. All right, but what is at this point? If you look at this integral here, what is difficult to understand? If you replace the sigma prime of t with a different parameterization of a same path, if you're going faster, for example, like that, does this one change or not? It does not change. If you look at this integral, it's not easy to understand. But if you look at the Riemann sum analysis, there is some explanation in there. Yes. That algebraically more integral friendly one, even if it is not constant speed, right? Yeah. Because the answer is the same. Yeah. All right. Let's actually calculate. I want you to look at this A and B and figure something out. These are two separate thing. So I'm going to call that one sigma A. I'm going to call that one sigma T. Sigma T. I want you to write down everything. There's a vector field. Write that down. This is going to be an exercise. Vector field is yi minus x plus xj plus k. And this cause, not free fall. Usually free fall doesn't cause this type of helix. So the best way to understand is, and there's a wire and then it's moving along. It's fixed to that wire, but this force field, creates some sort of force along that direction of the wire, just like in that example and exercise. All right, let's understand phi first. So the meaning of phi, we understand is a force field. If you go to like 1, 1, 1, that's a position in XYZ space, right? What kind of force is assigned here? Just arbitrary picture. The force assigned here is 1, negative 1, 1, right? So what is the magnitude of this force? Yeah, root 3 Newton. That's how much force is along that direction of 1, negative 1, right? Everybody understand where the root 3 come from? The length of the vector. Force vector, the length indicates the magnitude of the vector. Fair enough? If you go to different position, like 0, 0, 0, what is the vector assigned there? 0, 0, 1. Here is a k is 1, right? 0, 0, 1. So that's the force you're going to feel upward, right? So what is the magnitude of this force? So it's 1 Newton. That's the meaning of this one. Wherever you go, you plug in that xy coordinate in there. It tells you how much the force is applied to that position. Fair enough? Yeah. Just like gravity. If you go further away from the Earth, you feel less gravity, and towards that, you feel more gravity and stuff like that. All right. So I'm going to write the part A with the sigma t being like this: cosine t sine t t divided by 2 pi. That's one path. The second one, I'm going to use tau. Tau t is cosine t cubed inside. That's what they mean this one. Sine t cubed inside and t cubed divided by 2 pi. Alright, this looks like helix, right? Cosine t sine t, that's the projection onto x and y plane. And t rises constantly. So that's a helix that showed you earlier. How about this one? If you cube it inside, how does that change this cube? Same path. That's the important thing. If you just substitute this one with u and u and u divided by 2 pi, don't you find this is exactly the same thing, right? So they pass through exactly the same thing, but in different fashion. This one probably starts slow, t cubed. Later, it's going to pick up a lot faster. That's what t cubed behaves. T cubed stays down like this and getting really faster. T is just always constant if you compare the graph of t versus t cubed. So it is actually the same path, right? And ended up at t equals 2 pi, 2 pi plug it in there is 1, right? If you third root of 2 pi, you plug it in there, you end up at 1, 2. So even the initial point and terminal point is exactly the same. Make sense? All right. So if you integrate, if you compute the line integral along that path, what do you expect? They should be the same. And we're going to witness that by actually calculating these two things separately. Okay? So let's do it. Let's do part 1. Let's formulate it together. How does it go? The line integral of this one is t0 from 2 pi, right? Correct? And let's write that down. Phi of, what's inside there? Yeah, sigma t. The r, the position of this path. So it's a sigma t. The position is sigma t and the vector in there at that position. Force field. And what is the operation? Dot product, right? And what do you multiply? Velocity, the orthogonal projection towards the velocity there, right? And then dt. So if you calculate this one, if you expand them out, it's just a one variable scalar function. And you're doing one variable integral. This is what you have to calculate. All right, let's do it. All right, how was it? So I didn't immediately replace this y and x with this thing. I first expanded, write it like this, and as I multiply, replace it, seeing that that's simply in there. So that's all right. But I identified as x and y and z. It's not just free. It is actually parameterized. The position in there. These are x and y position, parameterized by this. So I wrote it in that way, and this is sigma prime t dot product. So when you dot it with this one, y was a sine, so negative sine squared. Dotted with that one, a negative cosine squared. And this was simply 1 over 2 pi. So fortunately, we got negative 1 here. We didn't have to do any trigonometric integral, right? Sine squared plus cosine squared. So it's just negative 1, 1 over 2 pi. There was no t in it, so it was simply 1 minus 2 pi in there. Okay? This xy business makes sense? Yes? Yeah. Any question? The whole thing. November 16th. I'm going to copy it to the next page. I'm going to explain more. Alright, how can you make sense out of this negative number? Don't you think is 1 minus 2 pi is a negative number? Right? Suppose this is only one source of a force, right? Suppose there's a wind blowing the second source of a force. So if that's only the one source of the force, it's kind of moved toward to the whatever the force field is directing, right? Think about if you throw a ball in the air in the vacuum, if it is pulling down, the gravity is tend to come back down after losing the momentum, right? But if that means it actually moved complete opposite way because of the other sources. This is not a free fall. This is an arbitrary, just with my arm I push it along, but there's always this force field acting on that, right? Think about moving that furniture on the floor, even though there's a zero forces acting on that total, but there was something else always in there. So if you separate that, so that's what it means. It's actually, it moved against the direction of the force field on average of this path. That's what this means. There's other forces that moving this one actually on that direction there. Yes. Right, if there's no other forces acting on it, it's called free fall. In that way, that you definitely must have a positive number in there. Yeah. Yeah. Well, actually, if you throw it upwards, momentarily, it is moving opposite direction of the gravity, so you still get a negative number. Yeah. Yes. Yes, that's why you have to separate it and only talk about, you know. Yes, you can do that. Yeah, but it is kind of awkward notions for sometimes. But if you have to compute the total work done by all the forces involved, whatever that, if you add them all that, and that's the answer. It could be 0, right? But it may not be. Yeah. For example, if there's internal combustion and it turns out to be 0 because there's no other external forces, it's supposed to all cancel out and things like that. So if there's no awkward additional outside forces, usually the total work, all of calculating all the forces, it turns out to be 0. Some sort of conservation is described in that way. Yeah. Okay? Makes sense? Out of this negative number? Simple example is to throw a ball upward. It's momentarily from the beginning and to when it reaches the top, the work done by the gravity to that opposite direction, it's going to turn out negative. Yeah. All right, let's do part B. And you already know the answer, right? Answer is supposed to be 1/2 pi. There might be some technical difficulty, though, to calculate that. Let's formulate it together. How does this formulate it? 0 to, yeah, cube root of 2 pi in there, right? And here is still y negative x1. That doesn't change, right? That's the position. How about the sigma t? I'm going to leave it at sigma t. You're going to fill that in. Oh, this is tau t, right? So I'll use different letters. So tau prime t and dt. Let's spell out x and y and z here. What is x coordinate inside this integral? Cosine of t cubed, right? Different parameterization. And sine of t cubed? Z? T cubed divided by 2 pi. In there. So once you understand this much, your goal is actually calculating this one variable integral, dt integral. Was that okay? No? Any question about integration? But let me add further explanation of how to actually do this one in general so that you understand this independence of a parameterization. Is that as you have this further composition inside the argument, it pulls out this derivative of t cubed everywhere, right? And it's a scalar multiple. You can pull it outside, squared, and make a u substitution of u equals t cubed. Then this will be simply sine u cosine u, and is 1 over 2 pi. And as you do the substitution, you have du dt being 3t squared, right? When you do u substitution, you multiply the reciprocal and canceling this one out. So you can easily enter from here by doing the u substitution to 0 when t equals cube root of 2 pi. If you plug it in there, you get just 2 pi, right? And then you have y negative x and 1, and this dot product, and this 3t squared is cancelled out with this u substitution. So you're left with sine of, now this is substituted with a u, and this is cosine u And after this pulled out and cancel 1 over 2 pi. And here is the du after these 3t squared and the reciprocal of that cancel out each other. Now this is exactly the same as before with the dummy variable u, right? So that's the same as before, so you can actually enter the answer quickly by doing the substitution early on, not expanding and actually integrate. But this is in general what happened. If you have one parameterization, if you further compose it, you can make the quick u substitution with a further composition. They cancel out as through the chain rule and the substitution method and go back to the original one. So this is a direct proof that this doesn't depend on parameterization. Alright? So that's example is geared toward to that. There are two different parameterization of the same path. They end up at the same thing. Right? Any question? No. So this one's going to be easy. So they summarize it like this: independence of a parameterization, and see if this makes sense. And after all this discussion of, independence, there. Given phi, position-dependent vector field, sigma, that's actually the parameterization, how fast you're passing through that thing in there. And they're saying, if you have calculated like this, and if you further compose it with, just like we did, instead of, u in there, you put in the u cube in there, right? Just like we did before. Then it's a different parameterization. If you go through a different parameterization like this, with the different one in here, sigma 1, and all doing the derivative with respect to u, then these two will end up with the same thing. If you have any two parameterization, I'm just going to overlap like this, same path, if you pass through certain way, that's, let's say that was sigma t, and if you pass through in a different way, that's a sigma tau t, the different way of passing through the same path, and this one is a claiming, then I also claim that as a tau t is equal to sigma of some composition inside there, like this. You can always pull out, of course if you compose it, it's going to be a different path, but any arbitrary different path will be constructed out of further composing with a given path like this, so that it takes care of all the possibilities. Alright? So it doesn't matter how you pass through. I'm saying that several times today. But what do I say here, down here? Yeah, if you pass through like that, but if you pass through opposite way, then it's different. If you pass through the same direction, you started here, you end up at there, it's okay. But if you started here and end up at there, it's going to be different. How different? Just a negative sign. That's all, right? A negative sign. Even if you're going path through like this, a constant speed, even if you do some crazy thing like this, you repeat the path back and forth because you lost, and then going forward, the answer is the same. Why is that? Because they cancel each other. Because going backward and this opposite sign, the integral cancel each other. So whatever the odd number is, to go forward, you have odd number of zigzag to getting forward. So they all cancel out, leaving one path left it in there. So it is the same as just going straight forward. Right? So this is called path independence. Alright, I don't think we have time for this, so I'll stop here.